Well, good evening, everybody. Welcome to another Cafe Scientifique, another edition of our lockdown scientific extravaganza. I was actually just looking out the window today, and this is probably one of the first evenings of Cafe Scientifique when I've actually been pleased to be inside, what with the weather we're experiencing. Just let me provide you, in addition to welcoming everybody, just a sense of what to expect this evening. So, as I mentioned before, my name is John Willis, and I'll be helping to host this evening. I'm just going to give a brief welcome and orientation, and then I'm going to turn over to this evening's speaker, Karun Thanjavur. He's going to speak to you for about 45 minutes, and then as we get to around about 6:50 this evening, he'll be wrapping up his talk, but then we'll have at least 10 minutes available at the end of the talk for your questions. And what seems to work well for everybody is using the chat window that's available. Just in case you're not familiar with some of the controls for Blackboard, to access your chat window, just look to the bottom right of your browser. You'll see a little magenta tab there with two arrows. If you click on that, that will open up a little sidebar. And then what you want to click on is the little speech bubble at the bottom of that sidebar, and that will give you an opportunity to type in questions. So that's a great way of interacting once we get to the question and answer session. Let me also, while I am thinking about it, just give you a quick heads up for what to expect next Tuesday. Remember, we have two Café Scientifique per month. The one held tomorrow, same time, same place, same link. Will be given by Rebecca Hoff, and the title of her presentation is going to be "It Takes a Village, Building a Research Community to Tackle Problems in Disease, Environment, and Education." So you've got that to look forward to next week. I always have so many things to remember, so I know this often is disjointed, so apologies, but the other thing I would alert you to is, of course, you are all watching this presentation live, but we do record all of our presentations, and they are available on our YouTube channel, which is UVic Cafe Sci. And so if you want to recommend this to colleagues, or if maybe a partner or friend has missed this and wants to catch up, that's a great place to direct them to. So the evening speaker is Karun Thanjavur. He is actually our senior lab instructor in astronomy in the Department of Physics and Astronomy. And among his many duties, which covers teaching our undergraduates, a large amount of outreach using our telescope for teaching local school groups, he also helps to teach a graduate course in machine learning and advanced computing. And it's that passion that Karun is going to share with us this evening. So the title of his presentation is Deep Machine Learning with Neural Networks, the Second Industrial Revolution. All yours, Karun.
Thank you, John. Yeah, thank you, first of all, for this invitation to share my interest in machine learning and to kind of introduce this field of machine learning, which is bringing about some fundamental advances and developments in many areas of research and application. And that is, I hope during the course of this hour, I'll give you a flavor for what it is and kind of demystify it so that going forward, people will follow up on some of the leads I'll provide during this presentation and get a deeper understanding of this new field, which is bringing remarkable, as I mentioned, not only in research, but also in applications. It is really unnerving, I think, to be talking to my own computer screen instead of to a room full of friendly audience. So John and I were just discussing, if you have any questions during the presentation, please feel free to post them on chat. Sometimes it's easier things clarified immediately than wait till the very end, just so you can follow the flow of the presentation. But if the questions can wait till the end, I'll be happy to answer them at that point as well. And again, as John mentioned, it's been a rainy evening, and normally, people wouldn't have had the chance to actually come to Herman's Jazz Club to attend the Cafe Sci, but now the warmth of their living rooms, all of you can join, and even friends from elsewhere are dialing in. So that's the advantage of doing things online, I guess. So let me start my presentation by sharing a personal experience, a story, and I think many of you will be able to kind of relate to it as well. So I'm an astronomer, and at times I go to the observatory on West Sandwich Road, the Plaskett Observatory, and do observations there for one of my science projects. And this happened a few months back. I was just getting ready to go and spend a night observing. But being in Victoria, the first thing we do is make sure that the weather is cooperative because things change very quickly. So I looked up what is called a clear sky chart, which kind of provides a forecast of what to expect in the upcoming night. So it gives cloud cover, transparency, the chance of rain and wind speed and such things. But while I was glancing at that page, the other thing that caught my eye was this little ad off to the side showing a bunch of backpacks. And I was quite puzzled why on this weather page there would be this ad with backpacks. And then on reflection, I realized that just a couple of days back, I had been shopping online, looking for backpacks for a backcountry trip. And the ad was not from the store where I was browsing their online catalog. But what was remarkable was it wasn't just popping up random backpacks like school backpacks or day packs, but in fact, it was showing backpacks similar to the ones I had been looking at, the bigger backpacks that you use for multi-day trips. And then I realized, that my search on the web is being monitored most likely by a neural network, which has built a model for my search preferences and things that I'd like to shop for, and was then supplying me, kind of enticing me to spend my dollars on all these other things. It was actually recommending things for me. And that is nothing but another neural network. And all of us, I think many of you would have had similar experiences where you've been looking at something one day and then a few days later, you get an ad which is very kind of tuned to what you had been searching for. And all that is thanks to neural networks. So people have used it for recommending items as well. So here's the roadmap of what I'd like to talk about today. Talk about what seems very futuristic, and then we'll dive a little bit deeper and look at the neural network. Just see what happens under the hood. I'll talk about some aspects of how a neural network is taught to perform as it does, and then finish up with just talking about one aspect of research in which I'm using machine learning, just to kind of put things in context as well. So even though AI and machine learning seem like something futuristic, in the next couple of slides, I'll try to convince you that AI and machine learning are all around us. We use it day to day, sometimes not realizing that actually what we're using is actually a neural network. And here's a slide which kind of shows you some of the examples. So every time you hold up your cell phone to take a picture of perhaps friends, you notice a little box appears around their faces to kind of tell you if things are in focus or not. So there is facial recognition happening, so it's actually an object recognition, and it puts a little bounding box so that you'll know that the lighting is good. And sometimes after you take a picture, there's a little pop-up window which says, oh, there was probably an eye blink or something blurry. So there is a neural network monitoring what you're doing, the picture that you're taking, and advising you on how to improve it. And once the picture is taken, you can also have neural networks which will tag the pictures for you, as in this picture. So if you had a bunch of pictures where you're told what your friends look like, the neural network will actually write a little caption of the picture for you. It'll recognize who the people are in the picture and do the captioning. We've also quite often used Google Translate to do translations. So here I just put in the title of my presentation and asked it to translate it to French. And it did a very excellent job. It's not just word-to-word kind of translation. It's the way a native French speaker would actually translate the title. And of course, the constant barrage of advertisements, the recommended systems, which tell us what we should be spending our hard-earned money on. Every time you're on the net, there's always these ads, and the ads are very finely tuned, and that's because there are neural networks which have been designed to look at your search patterns and recommend things that are of interest to you. So all these are applications of neural networks, that we have all experience, we see in our day-to-day experiences. And just looking ahead, the self-driving cars, it used to be, something like a science fiction movie, but we see them on the road already. I was in California just before the pandemic hit, and walking around the streets, quite often I would see these self-driving cars just wandering through the streets. The driver would be sitting in the driver's seat with hands folded. The car would be driving itself. And you can make them out because of their big dome on top, the LiDAR dome. That's how you make out it's a self-driving car. And there are models now which have been certified to go on the highway. And I was talking to an engineer working in the field, and he mentioned very soon these self-driving cars will become so safe, probably even safer than a human driver, that the insurance companies will make us pay more to drive our own cars. They will insist that the machine take control because they're much safer drivers. And I was just thinking to myself, perhaps if you want to drive your own car in the age when everybody else is doing the automated driving, then perhaps you'll have to put a bumper sticker which says human at the wheel, so that the rest of the machine-driven cars will pay extra attention to the human-driven car. So that's how safe things are going to be and how quickly this technology is advancing. So that's all on the application side, but what about research? And I will just kind of highlight the popularity of machine learning in research, taking the number of papers which are published every year, which have something to do with machine learning, either using machine learning for a particular project or actually directly talking about some algorithm in machine learning. And this is taken from the preprint server where people post their papers which are about to be published. And as you can see, the number of papers in machine learning related subjects have grown exponentially since the 2000s, and last year, which was the year that I last took this statistic, it had gone off the chart at over 3,000 papers, and that's about 2 papers per day just in astronomy alone, that using machine learning for a particular application. That's how rapidly things are being done, and this is not just in physics, but in almost every branch of research and application, be it music, language, economics. People are finding more and more applications for machine learning in all areas of study. So where did it all start? So we'll have to roll the clock back a little. So AI, artificial intelligence, has been around ever since computers were invented, I think. People have always wondered, can we teach these machines to perform like humans? And the field of AI had its kind of up and down growth till about 2000. There were some breakthroughs, and then things would slow down, and then things would pick up again. And at the end of the last century, the 20th century, things had kind of ground to a halt because there was one hard problem that people had not figured out how to solve, and that is image recognition or object recognition. So, for instance, I have this cute picture of a puppy, and if I were to ask anyone in the audience what it is, we'll have no problem, figuring that out. It's not an issue at all. But if I were to ask you, how do you know it is a puppy? What are the rules you're using to know that it is a puppy? And I ask that question because if I were to teach a machine to identify it as a puppy, I'd like to turn the rules that you're using to identify the puppy and write a program that will use the same rules, so that way the computer can actually figure out that it is a puppy. And just as a joke, I said, back in the 2000s, if you had Siri and if you were to ask Siri, show Siri this picture and say, hey, what is this? Siri wouldn't have been able to answer that question. Something that even a child can answer, Siri would have been completely stumped. And that was the issue the computer scientists were facing, is how do we teach a computer to identify something as simple as a puppy in a picture? So the initial attempt was to basically turn human intuition and expertise into a computer program. So they built what are called expert systems. They asked the experts in the field about how they went about with the identification or solving a particular problem. Then they would build these heuristic kind of AI models. And there were special programming languages in our platforms like Lisp and Prolog that were designed to take that logic that these human experts were using and convert it into a computer code. And again, just as an illustration, I've kind of put a few lines of code on how they probably would have gone about it. For the case of the puppy, perhaps look at the nose, somehow identify where the nose is, and if the nose is black, if the eyes are black, and if the ears are pointed, then perhaps it is a puppy. So this is, of course, I'm simplifying things dramatically, but that's along the lines on which they worked on. So they used the logic, what they thought was the logic in a human mind, and built the logic into a computer program and hoped the computer would be able to perform as a human did. And it was reasonably successful. They managed to get things done up to a certain point. But if you change the features even a little bit, for instance, looking at this, none of us will say it's a puppy, even though the features are very similar. Here too, the nose is black, the eyes are black, the ears are pointed, and the tongue is sticking out. But this is a cat. But if you had built the program around the logic that I was mentioning earlier, your computer will say it's a dog again. So that was what was happening. A small change in the features, and the computer would fail. And then you'd have to tweak the program. So it didn't seem to be robust. The solutions people were coming up with didn't seem to be robust. And the biggest breakthrough happened in that area of computer vision around the year 2000, where for the first time, Yann LeCun actually introduced this thing called the convolutional neural network, or the CNN. And I will kind of highlight how that worked. And very quickly, computers learned how to do this object recognition, from the stumbling blocks of the expert systems. People moved into the CNNs and were able to solve the problem very quickly, and advances since then have been very, very rapid. And so rapid that I have a plot here that shows the advance in image recognition since the time that the CNNs were introduced. This is what is called the image classification challenge, in which the computer algorithm is presented with 1,000 different object classes. So earlier I was just talking about puppy identification, but here the computer algorithm had to identify 1,000 different classes, and this had to be done using an image set well over 1 million different images. And in the early years, the graph runs from the year 2010, you can see that the error rate was about 30%. In other words, the algorithm went wrong once in every 3 pictures. It managed to get 2 right, but the third one was wrong, on average. But as the years, as the developments advanced, you can see how quickly the error rate diminished. From about 30%, in about 5 years, it had gone down to 4%. And if you look at the last bar, it says human. So that's the error rate if you were to ask a human to do the same challenge. Okay? So humans get, on average, 1 out of 20 wrong. Okay? So that that's the error rate of the humans, but the machines were doing better than the humans. So the machines had beat the humans at this game of image recognition in just 5 years. And this stops at 2015. CNNs have continued being developed. So you can imagine how small the error rate is right now. So this is the kind of technology that is in your cell phone camera, which then puts the bounding boxes. Okay, so it does the segmentation and is able to identify faces very easily. For it, it's a trivial task now to actually identify faces and tag the names and all that. So that's how quickly the field has developed. And this is just talking about CNNs, but there are many other flavors of neural networks which have also come onto the scene and which are making very big advances as well. So what is the difference between these neural networks and the expert systems or the classical modeling that was done earlier? So to illustrate that, what I have here is a pictorial representation of the classical modeling. So the way, for instance, since I mentioned weather forecasting, let's take that for an example. So if I want to forecast the weather, then I make a bunch of measurements. I look at, I don't know, wind speed, wind direction, what the relative humidity is, what the temperature is. These are all my measurements. I use those measurements in most likely some kind of a mathematical formula, which converts these measurements into a prediction, which is whether it would rain in the next few hours, for instance. So that is my output or the prediction. And this model is usually a mathematical model. So other than the measurements, we also have what are called modeling parameters or coefficients, which are which assign relative weights to each of the measurements. So it decides which measurements are more important or which measurements are less important. And those coefficients are also built into the equation itself. So once you use some limited data, so if you've done this model a few times, you kind of figure out what the values of the coefficients should be, and then you can use it to make predictions going forward. So all you need to do then is make a bunch of measurements, plug it into the formula, and it'll give you a prediction. Okay, so that's the way classical modeling was done. In this case, I kind of mentioned a mathematical model. It could also be a statistical model, a logical function, so various types of models that could be used. But this is the general framework, so you kind of build a model, you tune the model using a limited data set, and then use it to make predictions. But in the case of neural networks, that has been completely replaced. It's a major shift in the paradigm. And here what we do is we use lots of data, and that is because it's the era of data. So everything is digital, everything is kind of stored in servers and all that. So we have access to lots and lots of data. And let's again staying with the example of weather prediction, we have weather data for many, many decades. And we also know that every day that the weather parameters were measured, we also know whether it rained the next day or not. Okay, so we also know the answers or the labels. So we have lots of data. We also know what happened in the future at that time. So what we do is give the computer a network architecture. Okay, so we just don't give the computer the data alone, but we also build something like an architecture, the neural network architecture, just the bare bones of it, and then ask the computer to use the architecture along with the data to make its own rules. So we don't build any mathematical function. The computer does it internally. So it makes its own rules internally using the data and the network architecture in what is called the training phase. And once the computer is fully trained, going forward, all you need to do is just give it the measurements and it'll be able to make the predictions, very much like your mathematical function. But in this case, there is no mathematical function. The computer made its own rules. Okay? So that's the way machine learning works, is the computer teaches itself on how to make predictions we don't impose any mathematical function on it. So at the bottom of the panel, I've kind of shown you the architecture. So we just give it an input, a bunch of measurements from the past. We also give it a bunch of answers. We give it a general architecture, and then we train that network. And I will explain what happens during the training. And once the training is done, all you need to do is give it the measurements today, and it'll make a forecast. And we're beginning to find that its forecast is probably more robust than the earlier mathematical models that we were using. It's able to do things much better these days. So in machine learning, there are two kind of general classes of neural networks. The first is called an unsupervised neural network. And in this case, the data that we use for the training has the measurements, but it doesn't have the answers. And all it does, well, what it is very good at doing is kind of segregating those measurements into different classes. Okay? So for instance, again, taking the example of weather, it just classifies the weather into rainy days or sunny days or cloudy days based on the measurements themselves. Okay? So that's one way that we can look for correlations within the data or clustering within the data, and those are called unsupervised methods. The other one that I've kind of alluded to so far is where the neural network is trained with a set of measurements, but also the answers so that it can actually make a prediction, and those are called supervised methods. And in this presentation, I'm just going to be focusing on the supervised methods. So it'll be a completely different talk if I'm talking about unsupervised methods. The approaches are very different. So for the sake of today's presentation, I'll be talking about the supervised methods, and those are the ones we see most often. Okay, so they're the ones which are much more popular and much more widely used. So I've touched upon this thing called training a network, and it's in some ways parallel to the way we train a human network, the mind, okay, the brain. So I've shown on this slide, how we train a child. Okay, so as you can see, at bedtime, a parent is sitting with a child and going through a storybook and pointing things out, and kind of looking at a picture of a dog, says, hey, that's a dog, or a cat, or whatever it may be, or an apple. So the child, initially, it's just gaga goo goo, so the child's brain is completely untrained. So it's listening to the parent and identifying the picture with a word. So it's learning to identify just by the trial and error. So perhaps when the child and the parent then go to a park, they see a real dog, and again, it's reinforced. So this is what a dog looked like. So this is done repeatedly for many, many classes over a long period. And right now, we have a 2-month-old at home. So we are very much in this phase. So every time I sit with my daughter Annabelle, with a book or something, I'm repeating things, and hopefully, so the information is going into the child's brain. So as this training progresses, so initially, it's just gaga goo goo, and then that converts to, hey, animal or something. The baby says animal, and then it refines it, and then says doggy, and then perhaps, golden shepherd, for instance. So at different phases, the learning becomes more and more refined as the training progresses. And once the training is done, the child is able to read a book and not only identify dogs that the child has seen before, but also extrapolate to other classes. Okay, so look at things, pictures that the child hasn't seen before, and yet identify it as a dog or a cat or a llama or whatever it may be. Okay, so that's the human training that happens. And in the case of a neural network, something similar happens. So what we do is, in the case of a neural network, we use tens of thousands of images, which is then used as the input to the neural network, which I've shown on the slide. There's a bunch of blue dots. Each of those blue dots is called a node, and I'll tell you what goes into a node. These nodes are arranged in parallel to form what is called a layer. And in the case of modern neural networks, there are hundreds of layers, so very much like a human mind. There are layers of neurons. So the same way we have layers of nodes working in parallel and also in series. So the input pictures, the information in the input pictures is kind of synthesized by the neural network, and it produces an output, which is a prediction saying whether the input picture is a dog or a cat or whatever it may be. Very much like how the human child was able to identify the pictures just by repetition. We do the same thing in the case of a network. We use these hundreds of thousands of images through the network repeatedly in this process of training. And at the end of the training period, the network is then capable of identifying these different classes. In the case of the human child, it takes years, but we have very good computing systems these days, the so-called GPUs, or the graphical programming units, these computers that can handle large amounts of data in a very short time. So the training takes, from a matter of a few hours to a few days or so, depending on the complexity of the problem. And that's how long the training a neural network takes. And at the end of the training period, the network is capable of making predictions with a high degree of accuracy. So what do these nodes look like? Again, drawing parallels with the biological system. Shown here is a very simple cartoon of a neuron. What we have, the neurons we have in our brain. So each cell, each neuron has a bunch of inputs, so which I've called dendrites. So they bring inputs either from sensory organs or from other neurons upstream. So all those inputs coming in through the dendrites, they are processed by the nucleus, the cell body. We don't fully understand what goes on in there. Some kind of a magic happens, and the inputs are somehow synthesized. And if the sum of the inputs reaches a certain threshold, the cell fires, or there is an activation potential, and that output then travels down the axon, which is the output from the neuron, and that passes on to the neurons downstream of this particular cell. So that's the basic. That's how, in a very simple way, the neuron works in our brains. In the case of a neural network, the basic unit, the node, or they're also called neurons or perceptrons, act very similarly. Okay? So in this little cartoon here, the x's are the inputs, and the inputs are either the measurements that we use as the input values. Going back to my example of weather, it could be the measurements we made, like wind speed and wind direction and temperature. Those are the inputs. Or it could also be the output from nodes upstream. Okay? So because, as I mentioned, these are in sequence. So one node, the output from one node goes to the next node. So the excess can also be coming from other neurons upstream. So what the cell body does, in this case, the neuron does, is it weights each of these inputs. Okay? Weights as in decides which input is more important and which input is less important. Those are assigned certain weights. And so all these inputs multiplied by the weights are summed together. And if that sum is above a certain threshold, there is an activation. So a signal which is usually 0 switches to 1. Okay? So that is very much like the activation potential of the neuron itself. And that output then goes to the neurons downstream. As I mentioned, these layers are arranged in sequence. So the output from one set of layers, one layer goes to the neurons or the nodes in the next layer. Okay? So very similar to the way we picture the brain working. Okay? So that's what a single node looks like. So in order to, for those who are keen to know, to get the mathematical details, it shows the node in a little bit more, with a little bit more mathematical details added. So the the W1 and the W2 are the weights assigned to all the inputs. The X's are the inputs. So each input is multiplied by its corresponding weight. It's all summed up together, and then it is passed to what is called a threshold function, where that's shown on the right here. So y equals 1 over, that's the threshold function. And graphically, I've shown you what the threshold looks like. So if the values are very low on the negative side, the output is 0. But as it approaches 0, it switches from an output of 0 to actually an output of 1. And this kind of a function is called a sigmoid. There are various flavors of these threshold functions. But that's the basic idea, is when the summed inputs reach a certain threshold, then the cell fires and produces an output. And that output is then passed on to the nodes downstream of this particular node. So that's what the details of one single node looks like. So what we then do is take these nodes and arrange them into layers. So we have multiple nodes per layer. They could be, depending on the complexity of the problem, we use multiple nodes per layer. And then the number of layers is also a parameter that the designer chooses. So how many layers do I need to represent my particular problem? So how much complexity is there in the problem? And that decides on the number of layers used. And in machine learning, it's called the depth of the neural network. So as the depth increases, we go from neural networks to deep networks. So that's where, and these deep networks could have hundreds of layers with hundreds of nodes per layer. So these are very complex networks to handle very complex data. But the basic structure, this is what the basic structure looks like. So input goes in on one side. The information in the input is synthesized by these nodes sequentially. And then at the very end, we get an output, which could be a prediction, like whether it's rain the next day or what the temperature the next day would be. So it can make predictions once the neural network is trained. But this is the basic structure of a neural network. And this is, of course, just one simple structure. We have many, many different types of networks as well. So far, I've just used pictures to kind of illustrate what the network looks like. But of course, in the case of a real network, everything is programmatically done. And for writing these programs, of course, these are very complex programs. Luckily, we have platforms which have been developed. And what is really attractive about this machine learning is that all these programming platforms, or most of these programming platforms, are open source. So you have access to these platforms for free. You can just download them off the internet and use them. Plus, there are plenty of online courses and tutorials and help pages where we can find information on how to build a neural network with lots of worked out examples. So overall, that's a very attractive feature about machine learning, is this open source nature, where people are very willing to collaborate and share knowledge. And in fact, that's how I got into it. Was, I don't have a classical computer science background. I'm more in physics. So even though I know how to program, I didn't have any background in comp science. But using these online resources, I was able to teach myself how to build these neural networks and actually use them in research. So it's very attractive. So those of you who are keen to get your feet wet, there are lots of online resources that you can turn to. And shown here are just two of these platforms, PyTorch and TensorFlow, which are very popular. So as I mentioned, the one that I use to illustrate a neural network is just one kind. There are very complex ones. The CNNs we've already seen, the convolutional neural networks that made this big breakthrough in the year 2000 is shown on the top left. Very often used for image classification, but it's finding applications in many areas now. Okay, so it started off with image classification, but it's being used in many areas now. The one on the left, the bottom left, the so-called GAN, or the Generative Adversarial Network, so the GANs. Here we have two networks which kind of work in tandem, or there is what is called a generator, which actually is one network which produces an output, and that output is monitored by a second network called the discriminator, almost like a teacher. So they work, they're supposed to be adversarial, but I take it to be more like a teacher, so the discriminator is constantly moderating the generator so that once the training of both these networks is done, the network is capable of producing an output which is just from pure noise. It is able to produce pictures, and that's one of the illustrations shown there. The four celebrity pictures. In fact, they are not celebrities at all. They are actually computer-generated graphics. So the generator and the discriminator pair were trained with pictures of real celebrities, and now the generator is producing what it thinks a celebrity should look like. So this is, of course, one of the kind of fun applications of GANs, but the same GANs have been taken and used for many real-world applications. Recently, I was listening to a lecture by Ian Goodfellow, who was the one who first proposed these GANs. And he said one of the recent projects he had been working on was to make the dental crowns. So if you go to a dentist, they, and let's say if one of your teeth have to be replaced with a crown, it takes about 2 weeks for a human to actually craft a replacement, what is called a crown. But now the generator can actually produce that crown in a matter of hours. So it looks at the rest of your teeth, it has a model of what your teeth look like, and it actually produces and then 3D prints the crown in a matter of hours. And apparently that was one of his recent projects. So these GANs, other than just producing fake celebrities, can also find applications in the real world and produce, can provide very useful output as well. And on the right, I've shown just a smattering of the different architectures people have come up with. Human imagination and ingenuity is just boundless, and you can see the complex networks people have come up with for specific applications. So I don't know where all these have been applied, but as you can see, there are many, many complex networks, network architectures that are available as well. So going back, so when I first showed you the insides of a neuron, I said that the inputs, the X's, are weighted by, or they're assigned relative importance or weights, the W's, but I did not say how the network knows how to assign those weights. So that is what happens during the training. So initially the network has just random numbers for weights. It's like the baby's brain. It's completely empty. So when you give it an input, it'll produce gaga goo goo, very much like a baby does, okay? Because it has no values, no real values for the weights. So what we do is shown in the next slide here. So we take, for instance, if we're training a network to identify pictures, we take a bunch of pictures and we pass it through the initial untrained network. So the network will do the gaga goo goo. It's just like tossing a coin. It'll just make random predictions. But we know what the correct answers are. So at the bottom, I've shown you what the labels, the correct answers are. So we compare the output or the predictions from this untrained network with the correct answers. And that comparison tells us how many times the network got things right and how many times it got it wrong. And initially, of course, there'll be many, many wrongs. And this wrong or error is used to compute what is called the loss function. So the bigger the loss, the worse the network's performance is. We use that loss to tweak the weights in the network. in what is called a feedback loop. So at the bottom, I've shown it with a green arrow. So the bigger the loss or the bigger the error, we tweak all the weights in the network. It's not done at random. The tweaking is done in a very mathematical, systematic way, in what is called a back propagation. So we go through the well-defined mathematical way in which these weights can be tweaked. So once the weights have been tweaked, we send another batch of pictures. And this time the network is partially trained, so the output will be a little bit better. So in other words, the loss function will decrease. Instead of having a big error, the error will be slightly smaller. And again, of course, we are comparing it to the known answers. We compute the error, and then we do the feedback again. And this time the tweaking will be smaller, okay? So we don't have to change the weights very much. And so this progresses repeatedly, iteratively, till finally the network, the loss function is very, very small or below an acceptable threshold. And then we say that the network is fully trained. So once the network is fully trained, then we can give it pictures that it has not seen before. And if the training is done properly, the network will make predictions which are correct, which are accurate. So that's the basic idea of training a network. So once a network is trained, we can also go in and visualize what the network has learned. And this is, these three pictures are from a convolutional neural network. So the initial layers look at features which are very, very kind of building blocks, like fundamental. It's just looking at slopes or edges or boundaries. And then in succeeding layers, it starts building complexity. So in the intermediate layers, it's able to identify features. In this case, it's used for facial recognition. So it's able to identify individual features on each face, so like the nose and the eye. And then in the final layers, it assembles the faces together. Okay? So as the information progresses through the network, the complexity of the information also increases so that the output from the final layers, it actually is able to recognize whose face it is. Okay? So that's the way these trained networks work. Okay? So starting from very fundamental features, it goes towards complexity as you progress through the layers. And that's why you may need many, many layers in order to capture a very complex problem, because you'll have to build from the basic features up to the very complex output. So just to wrap up, so this simply hard computer problem has been fully solved using CNNs. And, in fact, the CNNs are doing much better than even the humans these days. And so today, if you were to ask Siri, show Siri this picture and ask Siri what it is, it'll just give you a very detailed description that it's a 8-week-old golden retriever in a playful mood. Okay? So it won't just say it's a dog. So just in the last few minutes, one of the areas where I'm currently working on using machine learning is in medical research, working with collaborators from UVC, the Center for Brain Health. And what we're interested in is to help the clinicians, the doctors, identify concussions. And this is with sports-related concussions. Concussion or this mild traumatic brain injury is when, as shown in the cartoon, people go head-on, as in sports, ice hockey and soccer. This happens very often. So it's a very difficult thing to be able to diagnose or identify concussion. So what we're trying to do is build a neural network that the doctors can use in a clinical setting to help them in the diagnosis. Okay, so we're not relying entirely on the neural network. We're providing a tool for the clinicians to use. So in this case, what we're using as the input is actually EEG data, the electroencephalograph. So these are nodes that are placed on the outside of the skull, and you measure the electrical signals produced by the brain picked up on the scalp. So we have a training set. We have measurements of EEG from 62 adolescent athletes. So all of them are soccer players. So 35 of them are healthy. Okay, so they haven't suffered any concussions. So they form our base sample. And then 27 of their peers have had concussions. And so we know what a concussed EEG signal looks like as compared to a healthy EEG signal. And we are using that to train a neural network that hopefully will be able to diagnose or identify a concussion from an unseen EEG input. So to the eye, the EEG, the 64-channel EEG data is impossible to make out any particular features. So it is not as though we can just look at an EEG and say, this is a healthy EEG or a concussed EEG. So what I've shown here is from a healthy patient, and this is what a concussed, the EEG from a concussed patient looks like. And as you can see, they are just electrical signals, very difficult to interpret just visually. So this forms the input to our network. So we are using a special kind of a network. These are called recurrent neural networks, or RNNs. And what is remarkable about these RNNs is their neurons have, because they're looking at a time stream, a long sequence of data, they can also remember some of the data, they can forget some of the data. So they are looking at the whole time sequence instead of just the data from the upstream neuron. Okay, so there is a little bit more complexity in each neuron. And these RNNs are often used for natural language processing. Like in Google Translate is basically an RNN, because if you write an English sentence, it's not enough just to look at the word ahead of each word, but you need to look at the whole sentence. You should be able to see things right from the beginning to the end. So that sequential kind of data, these RNNs are very good at handling. So that's what we're using for the EEG signals as well, which is like the music of our brains. So that's what we have used. And in our results so far, it's very, very encouraging. So we're getting over the 90% accuracy in the work we've done so far. Of course, there is many more tests to be done, especially in healthcare. We need to be very careful about all this, but the results have been very, very encouraging. So taking that is used in language processing, we're applying it for medical research. So that's my last slide. So just to summarize, so these neural networks are a major revolution. Okay, so that's why I called it a revolution, is that it has fundamentally changed the way we look at data in a fundamental way. So these architectures are developing rapidly. People are coming up with all kinds of new applications and architectures to use. So as I mentioned, it's often used in astronomy and, of course, in every field, including creative arts. There are, of course, many ethical questions that need to be answered. So how much we need to be careful about how we interpret the results coming out of a neural network. And of course, all these development has been in the last 20 years. So we are still in the very early stages. Things are moving at breakneck pace right now. So it's nice that you're interested in learning more about it. And I strongly encourage you to stay tuned and learn for yourself a little bit more using the online resources. So thanks. That's my last slide. So I think I'll stop sharing so that I can see at least John and take any questions. So thanks for your attention.
Well, that was a great presentation, Karun. Thank you very much. As is tradition now at Online Cafe Scientifique, I will encourage our audience to give you a virtual round of applause by all raising their hand simultaneously. There you go. You get a crescendo of clicks and dings.
Thank you, John.
Thank you very much, everyone. Well, everybody has to sit there so passively when we're enjoying these online presentations, and there's no way to actually give feedback to the presenter. And so I think everybody likes an opportunity to at the end of the talk. what I would say is we're getting close to the end of the evening. So if I might be able to take one question on the chat if somebody has something they'd like to post in quickly. While we give them a chance to type, Karun, I guess I had a few questions as you were presenting, but just to give one quickly, how far away do you think we are from AI doctor, an
AI
AI,
doctor?
an AI family GP? How far away are we from that?
I think we're still quite a ways away, and that is not because of technology. I think it is more the ethical questions, so uh, we have to be very careful. Just to give you an example, I remember reading a paper where they had used a neural network to initially screen the applicants for a job, so trying to replace a HR person, at least the
Yeah,
initial screening person. And what they found was the neural network had the same biases as a human HR person. In other words, we know that there are gender-based biases, there are ethnicity-based biases and all that. The neural network had picked up those biases and it had the same biases as well. And that is because the data that was used to train the network came from a human being, and those subtle biases had been built into the training itself. So that's the kind of things we have to be very careful about with these neural networks. So before we actually hand over control to a neural network doctor, we have to be sure that we understand what that neural network doctor is doing. And there are ethical questions that need to be addressed and carefully looked at before we hand over control. The technology is very much there, but these are associated questions that need to be fully addressed before we get to that point.
no, that's a great point, and really addresses, I think, the key point, which is human oversight of
Yeah.
artificial intelligence. I don't know if you or any of our audience this evening have seen, there's this wonderful Netflix documentary called The Social Dilemma that goes into all of these issues, basically everything that sits underneath those backpack adverts that get aimed towards you. They have a very interesting and quite thought-provoking documentary on all of those ethical issues that surround at least that particular application of artificial intelligence as used on social media. So, yeah, it makes a lovely and appropriate sequel to your presentation, perhaps.
Great, thank you, John. Yeah, I should
Yeah,
look that up as well. And
yeah, so everybody can be quite well armed in the technical knowledge now when they go and watch that. So I'm always very aware that we all have busy lives and lots of things to get on with. So what I would say is if the audience doesn't have any questions, I think we've had a wonderful presentation this evening. Just before I thank Karun again, let me just remind everybody that these presentations do appear on UVic Cafe Sci, our YouTube channel, and we will be back with another fresh presentation next Tuesday. Same link, same time, and you will all be receiving emails in your inbox letting you know the details of that. So thank you very much to our audience for joining us this evening, and thank you very much to Karun for a wonderful presentation.
thank you, John. Really enjoyed it. Yeah.
All right. So, I did see a quick question came in, but I think unfortunately our moment has passed. Sorry for that questioner. But yeah, so I'm going to stop recording now, Karun.